Welcome everyone, and let's go. Today will be part review again, and but we're also going to explore something that we've done before and take it now into something that is new as well, where will be the start of some new work for us as well. Okay. Forgive my nose is a little bit nasal this morning, so if I'm sounding stranger than normal, it's because of that. Okay. So this particular case, excuse me. Right, so today we're going to review the properties of the unit impulse. This one is specifically the discrete time impulse, which we also saw in signals and systems that you can call the unit sample. And in the context of that, things like the you shifting around, the shifting properties, how we connect it to the unit step. And then we're going to talk a little bit about a couple of things with the system and impulse responses, and then get down to talking about something that is everybody's favorite topic, which is convolution. And you'll see it's a lot more straightforward than you've been probably believing all the way through when you deal with the continuous time version. But we'll get to that shortly. Right? And of course, if you have any questions, just try to catch my attention, and I'll try to clarify it at that point. Let me know if I'm not being heard too as well, in case the signal drops. Right, so the unit sample, remember the discrete time unit impulse is really a sample, a single value of 1 at time equal to 0, or at sample number equal to 0. Okay, the continuous time one, you remember, was an integral. It was defined as an integral of a function, right? And the integral of the function was 1, right? Meaning that the area of the continuous time unit impulse, it didn't matter what the shape looked like, but the area underneath the impulse was 1. So in other words, it could have been very narrow and extremely tall, which is in reality what we wanted, that it occupied next to 0 time, and the height was close to infinity. So it was a theoretical construct for us. But the idea is that we just simply didn't define it as something being 1, is that the area of that whatever that funny artifact was in fact 1. In the case of the discrete time world, it's a lot simpler. The discrete unit impulse or a unit sample is really a single value of 1, right? So it is a 1 at n equal to 0, right? Or time equal to 0, however you want to remember it. And of course, as usual, we can shift it around just like we can with the continuous time version. So if we delay it by 3, then the symbol representation is dn minus 3. This one here has been delayed by 3 samples, right? And remember that n is really shorthand for nt, right? And t could be 1 second, every microsecond, every hour. It doesn't really matter, and we'll see that coming along as well. Fair enough? So because of that now, if you want to see again the sort of relationships between other things that we know already, you can think of the unit impulse as the first difference of the unit step. Remember, a unit step was 0, let me get that point, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1. Okay, so if I take a unit step and then I take a unit step that is delayed by 1, so in other words, it is 0, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, and I take the UN minus 1 delayed from the UN, you get a single value left at the origin, which is in fact the unit sample, right? And remember, the analogy to that is that in the continuous time world, that the unit impulse, if you took a derivative of a unit step, that you got the unit impulse, right? Or the delta function as we sometimes call it. Yeah? So just to make that comparison that we mentioned in the first lectures, where the continuous time world talks of derivatives and differentiation, the discrete time world talks about differencing, right? And then down here now, in the second we can define the unit step now as a sum called a running sum of, as we have it here, a sum from minus infinity to infinity of delta m. Now delta m only exists at one point, which is at m equal to 0. So if I'm summing everywhere else, it will be naught plus naught plus naught plus naught plus naught plus 1 at m equal to 0 plus naught plus naught plus naught plus naught, so that the sum now will be 0, 0, 0, and then 1, 1, 1, 1, 1 all the way through. All right? And you remember, we saw this even way back in your calculus days, that integration, the approximation to integration was in fact summation. And as you summed and the intervals between the summations got closer and closer, then the summation became an integral sign. Yeah? So you're having the relationship here, or the analogy between the discrete time world and the continuous time world. Fair enough? Everybody with me so far? Okay, well, I'm hoping, I have my speakers off, so I'm hoping. All right, good, nice, there we go. Right, so this other property now, if we remembered from our signals and systems, if you multiplied any sequence by a unit impulse, it sifts out the value of the sequence at the instant of the impulse. So in other words, remember this here is 1 only at one point in time, which is at n equal to 0 or t equal to 0. So if I have a whole series of numbers starting, let's say, oops, right, 1, 2, 3, 4, 5. This is the n equal to 0 point. If I multiply xn by delta n, it's going to ignore this, ignore this, ignore this, and ignore this. So it's just going to pick out that value for me. Right? In other words, it's going to pick out the value at n equal to 0, which was 3. If I shifted this to some point here, then what it was going to do would have been to pick out the value shifted at that point in time, which in this case would have been 5. Right? And this is our sifting property of impulses. And in a more general case, I'll come to the last point in a second. In a more general case, we know that instead of a sequence, if you multiply, therefore, any signal by a unit impulse, it will select out the value of the signal at the instant of the impulse. And we call this process sampling. Right? So depending on where I put this delta n, I will sample the signal. And just back to this slide before, we can now use this property to build any sequence. In other words, I could build out a sequence by using this summation, sorry, this sampling or sifting property here. You look at it right here. So for instance, look at the sequence of numbers on top. Right? So I have xn, but in fact, I could dismantle xn by saying that, okay, this value is really x minus 2 by delta n plus 2. So it sifted out that value. This one here is really x minus 1 multiplied by an impulse at that point, right? So is this this one plus this plus this plus this plus this, so that we can make up the whole sequence up at the top by a series of sampled impulses or sampled values, which are the 5 below. So in other words, I could express xn as a sum of a series of sampled values where k is running from minus infinity to infinity. This is the shifting, this represents the sampling impulse that shifts from minus infinity to infinity depending on where k is, right? And I have a question here, does the form of this look familiar, right? And if you look at it carefully, you'll see you have an xk delta n minus k. This is a convolution type summation. Remember, the convolution that we know in continuous time is xt by ht minus tau, right? Or the other way, probably the more general form, x tau h at t minus tau, sorry, right? So you have the same sort of convolution behavior here, but we're seeing it very directly by using the property of how the impulse it has sifted out the values of the sequence, and we just add them up to get back the original sequence. Clear enough? Make sense? Yeah, no, maybe. Right? This one is easy to see, which unlike the continuous time case, the discrete time case is very easy to see. I mean, we could just pick the 5 samples here, and we can immediately see that the 5 samples are a collection of 5 individual impulses, and we added them up. Okay, so just summarizing the behaviors that we have, that the discrete time unit step is a sequence of values which are 0 before n equal to 0 and 1 for n greater than or equal to 0. The discrete time unit impulse or the unit sample is a single value at n equal to 0, a single value of 1, and 0 everywhere else. And that the relationship between the two is that the discrete time unit step is the summation, the running sum, right, which is the sort of discrete time version of the integration of the unit sample. And on the other way around, the unit sample is a difference, a first order difference between un and un minus 1, which is the discrete time versions. I should probably put this here. The discrete time versions of integration and differentiation, right? And also in the from the last couple of classes, we saw that the differences between in a periodic signal in the continuous time domain, that there was a period, if we identified a period where the signal repeated itself, then we could now classify the continuous time signal as being periodic. In the case of the discrete time, it's a sequence of values, and the values must identically repeat themselves after some integer, right, which is n. If we can find that integer, then the discrete time sequence had a period of capital N, right? And I told you here to separate in your mind what the signal looks like. In other words, what the envelope of the signal is telling you as compared to what the actual values are. The envelope could look like a sinusoid or a cosinusoid, which is telling you periodic signal. But from the discrete time world, the numbers, if the numbers are not repeating identically after some period of time, some integer period of time, capital N, then regardless of how it looks, it is not periodic, all right? And these two about finite energy and finite power signals, we will do, we'll talk a little bit more when we start to talk about spectrum analysis in a couple of weeks' time. But essentially, and you would have remembered this from some of your other courses, that remember the energy in a signal is really proportional to the square of the signal itself. So when you like a voltage, if you want to find how much energy in a voltage, you go V squared, and if it's dissipated in a resistor, you know, is V squared over R, for instance. And in terms of power, is how fast you consume that. how fast you dissipate or use that energy. So it's something that is averaged over time, right? In the continuous time world, of course, time is capital T. In the discrete time domain, quote unquote, time is functions of n and our sampling sort of interval. So if you're looking at it, if you have 5,000 samples, if n is 5,000 and you're looking at it every second, then you're looking at it for a period of 5,000 seconds. Or you could be looking at it for 5,000 microseconds, that kind of thing. All right, but we'll clarify that a little bit more when we start to discuss the whole concept of spectrum analysis. All right. So some little properties of systems. A discrete time system takes an input sequence, and that is the important thing here. That business in blue. Discrete time systems work on numbers, right? Values. So it takes a sequence in, does some sort of thing on it, and gives you an output, another set of values, another sequence of numbers coming in. And we can do that in two ways. We can do it sample by sample. So for instance, the input is a series of numbers, values, x0 to xn coming in. This is our system here. Whatever that transfer function is, a discrete time transfer function, and all of those things we'll be getting into. And some of it you know already. You remember when you did the Z transform that you could describe that, you know, 1 minus Z minus 1 over 10 minus Z minus 1 plus 4Z minus 2, for instance. So it's described in a discrete time domain. You remember the Z transform was the transformation of H, which was a difference equation, etc. And then when you worked it out, now you get a set of values coming out. So numbers in, numbers out. So some systems, many systems, do what is known as sample by sample processing. So as x0 comes in, the system gives me a value y0. x1 comes in, y1 comes out. x2 comes in, y2 comes out. Right? And most real-time systems would use this. Right? Real-time systems, meaning systems that trying to approximate almost how things happen in reality. In other words, you're not seeing much time delay. As something happens, you get an answer coming out. As you would realize, and from your microprocessor work on other courses as well, this is really an ideal, and there are very few truly real-time electronic or computer systems. There's all some sort of delay because it has to do some sort of processing. What it does is that depending on how it works, it fakes the processing in such a way that you, the user, or whatever is the other system down the road that is using it, for all intents and purposes, is getting the information immediately. So it seems real time, but it is not. It is always a good approximation, right? So values come in, and as a value comes in, a new value is generated. So this is sample by sample processing. Many systems do it that way. Or if the system stores the data, so all of the information, the input information comes in and is stored first, then the system now, if the system now takes that set of stored information and works on it as a group, is called block processing. Right? So the first one, the values, as the value came in, as the input came in, it generated an output. That's sample by sample. The other way is that if it is all of the information comes in first, it is buffered and stored, and then the signal processing system looks at the whole stored clump of data and works on it as a unit, and they call that block processing. This is what happens, for instance, in image processing. Right? So when you take, let me put an example, image processing. Right? For instance, when you take a picture with a camera, right? Your phone, you snap an image of something. The entire image, whatever is the resolution of the camera, that many pixels is immediately captured off of the image detector, the charge coupled device in the phone, and is stored as a big array, right? So many hundreds of thousands of values are stored, 1900 across and 1200 down, or whatever it is the resolution. And you have that block. And then to store the image and to create the JPEG image out of that, the software in the phone, in the camera, then takes blocks of that, big chunks of it, and works on it and creates the image that is now stored. All right, so that's a form of block processing, and is usually where the data is stored, where you're able to store the data and then work on it afterwards. Okay, you will meet both of them. Fair enough? Right, so another property, remember in signals and systems, we kept stressing this thing about linear time invariant. Same thing applies here. The linearity means that we can add up the individual responses to get the full response coming out. So if we have a system that does some function on a series of inputs x1 to xn, then what we can do, we can add up the response to each of them. So we can see what is the response to A1, X1, what is the response to A2, X2, and so on, and then add up those answers to get the final answer. That is if the system is linear. All right. Many systems are not, as we mentioned in other courses and in things like signals and systems as well. But what we can do is that for a range of operational circumstances, you can approximate the performance to a linear behavior and then work from there. All right, you would have met that too in your controls as well. There are certain assumptions that you can make so you can get through, you can get by within a range of operations and assume linearity. Same thing applies here. If it's not linear, then you have to use different techniques which are beyond what we will do in this course. Okay. The time invariant, of course, is that the input and output don't change, are not time dependent. So if I put a sequence of values today into my signal processing system and I get some answer coming out, if I were to put the same sequence of values tomorrow at this time, I should get the same sequence of values coming out tomorrow, right? If it changes, then somehow it is dependent on time. And of course, if you have a time dependent system, that's going to be very difficult to deal with, right? If you're dealing with, let's say there are certain complicated biological models, for instance. So as time goes on, the characteristics of the systems change, right? I mean, just a simple case of if you're if you're modeling sort of cell behavior, for instance, the cell's age. So an input today will give you an answer. The same input tomorrow will probably give you something different. That is not a time invariant system. Okay, but in our world and for electrical engineering and for control system engineering, we really do need the thing to be time invariant so that you turn on a power plant today and you get a certain sets of voltages and currents coming out of the generators. If you turn it on tomorrow, you're supposed to get about the same voltages and currents coming out. If you're not, and it is like human beings, that Mondays you get poor performance, Tuesday a little bit better, Wednesday, yeah, you're kind of in the middle of the week, Thursday you start to be really good, and then Friday the performance is excellent, and then you get nothing Saturday and Sunday. That would make our modeling extremely difficult. Yeah. And then causality, of course, the system only real-time systems, for instance, the output is only exists after you turn the system on. Okay, and we did mention this in previously in things like signals and systems, where you have stored data, right? The stored data, unless you explicitly say to ignore, if you will jump into the data and you explicitly say to store, to ignore everything that went before, stored data systems are typically not causal, all right? Because if you jump in and the example I give you is like a recorded piece of music. If you jump into the music in the middle, where the system is taking off or where the music goes from there is as a result of where it was a little while before. So it's not causal. It just didn't start there. Okay? So we will assume for most of our purposes that we're dealing with linear time invariant and causal signals. All right, if the system or the signal is not causal, we will explicitly say so as we go along. Yeah? Right, this is all revision, but explicitly directed to discrete time signals and systems. All right. So we just said that we can take any sequence and build up the set of build the sequence as a sum of weighted impulses. That was the slides a couple. Sorry, the slide a couple slides ago early on in this lecture. And specifically, when we talk about sampling, which we're going to do on Wednesday, please God, we'll see some of the implications of sampling and how that, how we space these things out, because there's a very critical bit of work that you have to do in order for this to work well. Okay. So a signal, if we are assuming a causal signal, any sequence can be built up as a sum of weighted unit samples, weighted impulses with the appropriate delay. And the delays are always integer multiples of some interval that you're looking at, right? So it's always an integer multiple of that. So n will be 1, 2, 3, 4, t, whatever t happens to be. You could never have a 1.1 or 6.7, that kind of thing. Okay? And if we are dealing with linear time invariant systems, then what happens now, and this is a little bit of how we led up to talking about continuous time convolution. Look at what happens here. If I put an impulse in a system, remember the impulse response of the system is a series of values coming in. So you put an impulse into a linear time and you get a set of values coming out. All right. If I put another impulse here, then I'm going to get another set of values coming out starting at this point here. Right. So you're going to get another set of values coming out. If I put another impulse here, then I'm going to get another set of values, right, coming out in response to that. And then if I put an impulse here, right, I'm going to get another set of values coming out in response to that one, right? So in other words, each xk delta n minus k, which are these values here that I might be putting in, generates its own set of impulses coming out, so that the overall response of the system is going to be a sum of all of these here. For every value of x that you have, it is going to be a sum of all of the individual responses coming out. Yeah? Make sense? In other words, the total system output is each of these, but for n equal to 0, which is the first set of the first impulse, n equal to 1, which is the second one, n equal to 2, which is the third one, and so on. Or alternatively, for those of you who do programming and so on, this is like a double loop, right? A double summation. So I could put the n here on another summation sign outside. So both of these are the same thing, right? This is the inner loop here that is running from k equal to minus infinity to infinity, and then the outer loop where n is running from naught to infinity, right? So the inner loop, so it runs the inside, then it runs the outside, and then it increments, runs the inside, increment, run the outside, and so on. This is also, we can also express this by, in this form, which is now what we know as a convolution sum. So that the input-output relationship of a discrete time system is the convolution of the sequence coming in and the system impulse response. Fair enough? Yes, no, maybe? Everyone following? Yeah? Good. Right, so again, and just to remind you all, it happens again in the continuous time world, and also the relationship between any input to our system and any output from the system is a convolution. So whether in the continuous time domain like we are here, once I put an input into a system, the output of the system is always a convolution of the input of the signals going in and the system response. That is how it happens in real life. What we did in the continuous time domain is that we use something like the Laplace transform that converts this process into a multiplication process, so that you could solve and model the behavior in the Laplace domain by using multiplication. But then when you finish, you have to come back to reality. If you want to do it without using the Laplace transform, and we did it, you remember in the continuous time domain, we did it where you flip and slide and you did the integration. We're going to see how to do that from the discrete time domain in a short while. Right? Right, and this was just saying that the order of the convolution, it doesn't matter whether it's hn convolved with x or x convolved with h, right? Which is, again, another important property for us. And just some characteristics here. Some systems, when you put an impulse in, they give you a response, which is a set of numbers that doesn't end. It keeps giving you a response going on and on and on and on. And they call those systems infinite impulse response systems. However, there are other systems where you give the impulse in, and then it generates maybe 100 numbers or 500 numbers or 50,000 numbers, and then it ends. But it ends. That's the important thing, and they call those finite impulse response systems. Now, one of the things you have to remember here is that this thing about infinite and finite is very subjective when you're dealing with discrete time systems. Remember things like the computer that you have in front of you, or your cell phone, and so on. Those are ticking along at several hundred megahertz per second. So 1 second in a calculation, if you're going along at 500 megahertz, for instance, a single second worth of processing can generate, in theory, 500 million samples. So if a system has a response that goes on for 1 second, it will generate 500 million values, but it does stop, right? It is finite. What we're talking about is systems that will not stop. And in the case of this, if you're talking about for a system, let's say, going along at 500 megahertz, if it goes on and the impulse response goes on for maybe 5 seconds, that may be enough to fill up the memory with data. So that sort of thing you would consider from the purposes of the system to be an infinite response. All right, so this one is very subjective. A lot of it depends on what you're dealing with. right? So a simple microprocessor like the Arduinos or the small PICs that are embedded in maybe a medical device that has a few maybe a few thousand memory slots. And infinite response will be something that generates 100 values for argument's sake. Okay, your laptop here with gigabytes of memory space and infinite response might be something that generates 2 gigabits of data. So something to be discussed a little bit later on, and we will come back to it because there are ways of handling both of them. Both of them have their advantages and disadvantages. And if you are constrained, then you have to approximate as with everything in engineering. All right? Okay, so let's spend some time now and look at this convolution equation. Right? So we are assuming a causal sequence, meaning that it's starting at k equal to 0. And remember, the convolution equation is that the output is the sum of the input sequence and the system response hn minus k. So let's just expand that a little bit. And of course, n going from n is 0, 1, 2, 3 until whenever this thing ends. So let's just expand this a little bit. Let n equal to 0. So that y0 is the sum from k equal to 0 to infinity xk h0 minus k. And if you remember, this is h minus k. And if you remember from when we did those kind of things before, h minus k is just simply hk reversed or flipped around in time, right? So that if I were to expand this, right, what I have now is that by continuing the expansion, I have, going back here a little bit, if I expand this now and let k equal to 0, well, k going from 0 to infinity, so what I have here is x, oops, x naught, right, k equal to naught, right, h naught, oops, this should be h naught, and then when k is 1, I will have x1 h minus 1, then x2 will be x1 h x2 h minus 2, and so on, right? So if you look at it here, this is the expansion that we when we expand for the value where n is equal to 0, right? Fair enough. Then we let n equal to 1 now, and if we expand that, we're going to have that y1 is now, remember k is naught, so it's going to be x naught h1 plus x1 h naught plus x2 h minus 1, and so we keep going on, right? And h1 minus k is hk delayed by 1. So we could keep doing that, right? All I'm doing, no big set of maths here, no integration, no finding area under anything, all right? And if you expand that, you get that y2 is x0 h2, x1 h1, x2 h0. Notice a little thing here to help you out if you if you want to expand. So for instance, y3. Notice these two things have to add up to this. So y3 would be x naught h3 plus x1 h2. Forgive me, I'm supposed to be using square brackets, remember that, yeah? Plus x2 h1, etc. So the two of them will keep adding up to 3. 4 would have been x0 h4 plus x1 h3, and so we keep going on, right? So you could keep expanding, but let's see how to do it like we did with the continuous time domain. Let's see how to do it graphically, right? And see how fairly straightforward this is, at least for a small sequence of values. So let's apply this. We have two sequences coming in. X, which is the input, which is 1, 3, and 4. And Hn, which is the system response, which is 5, 4, and 2. In other words, if I put an impulse at n equal to 0 on the system, it generates 542. Yeah? So I'm asking, the question is, well, what is the output now, which we know is a convolution of xn and hn? So what we do is that we write it down a little bit. Look, xk here, xk is 1, 3, 4. Right? Xk is 1, 3, and 4. Hk is 5, 4, and 2, but we flip it around. Remember, h minus k is 5, 4, 2. So we flip it around, 5, 4, 2. And you remember, we now start the first value, the first output, which is at y equal to 0, is x naught, h naught, which is this. So that's 1 by 5. X1, h minus 1, you notice I have no overlap. X2, h minus 2, you notice you have no overlap. So that the answer, the first value of the convolution is 5. Make sense? Yeah? No integration, right? You don't have to find no. Remember how to integrate under between t minus 1 and t plus 1, etc., right? Okay. So next one, y equal to, for n equal to 2, sorry, for n, that was n equal to 0. For n equal to 1 now, we have to shift everybody down by 1. So we still have the xk, which is 1, 1, 3, and 4. h1 minus k is hk. Remember, hk was here, 2, 4, and 5. We shifted it down. We shifted this way now by 1. So it is now 2, 4, and 5. y1 is x naught h1, which is this, which is 1 by 4, plus x1 h naught, which is this, which is 5 by 3, which is 15. x2, but it have no other overlaps here. x2 by nothing, x3 by nothing, right? So the second value of the convolution is 4 plus 15, which is 19. X3, for n equal to 2 now, we shift k down, hk, we shift it down by another one. So look at the zone of overlap here. The zone of overlap is y naught h2 plus y1 h1 plus, sorry, I'm missing, x naught h2 plus x1 h1 plus x2 h0. No other overlap here. So that is 2 plus 12 plus 20, which is 34. And the next one now we will put, we take the hk and we shift it down here. So it is now 2, 4, and 5. And this would be h3 minus k. And then we will put it 2, 4, 5. And this will be h4 minus k. And then we put it down to h5 minus k until there's no more overlap. Just like we did in the. So if you do that and you expand it out, the overlap ends at h5 minus k. You see that x is here. So after this point here, right, at this point here, there are no values of x and h that are overlapping. So if you keep working on the values now, the convolution has 5 answers: 5, 19, 34, 22, and 80, and 8. Sorry. Yeah? Make sense? Yeah, no, maybe it's the same flip and slide technique, except that here we have no integration to do. It's just flipping, multiplying, and adding up. All right? So you'll notice something here a little bit, and we'll point it out later on. Notice x has 3 values, h has 3 values. So together, there are 6 sample values. The convolution always has one less than that, right? So the convolution is going to have 5 values in it. We will see why a little bit later on. All right, so if X had 15 and H had 20, 20 and 15 is 35, the convolution would have 34 numbers in them. All right, so later on when you're doing these kind of things, if you're getting values that are more than one less than the number of values in X and H, then you made a mistake somewhere. Right? Now we have another approach that we could take. If we're dealing with causal systems, so causal systems means that H minus 1, H minus 2, etc. are 0. If I expand, this is what we did just now in the first 3 slides. So if I expand this, and if I'm dealing with causal signals, it means that I could forget this, forget that, right? Forget this too. So what I'm going to have is that if the system is causal and we can ignore H minus 1, H minus 2, etc., when I expand the convolution equation, I get that y naught is x naught h naught. Y1 is x naught h1 plus x1 h0. Y2 is naught h2, x1 h1, x2 h0. Y3 will be x naught h3, etc., etc. What I could do, right, which is what we have here, I could put this into a table because all I'm dealing with, I have no H minus 1, H minus 2, and so on. I'm dealing with all of the actual values that I have, H0 to whatever, and X0 to whatever. I could put this now into a table. If I put it into a table, notice what is happening. I put the X's across the top of the table, starting with X0, X1, X2, X3, in this case, X4. So I have a number of values here. And then down the columns, sorry, these are the columns. So the columns are X0, X1, X2, X3, X4, up to how many values we have in X. And the rows are H0, H1, H2, H3. Notice that I'm starting 0 here and incrementing in this way, right? Okay, so X and H. We call this a convolution table. And what I do now is in each of the cells here, I fill in the product of the row and the column. So here will be H0, X0, here will be H0, X1, H0, X2, H0, X3, etc. Right down to here, which would be H3 by X4, right? That's real complicated, yeah? And then what I do is that I sum across what we call the anti-diagonals. So what I do is that I start here now and I look, I'm summing, I got a different color here. So after, like the ones that we did before, we have 1, 3, and 4, which is what we just did, and H, 5, 4, and 2. Notice this is not reversed there. I put H this way and I put X this way. Fill in the columns, the cells, sorry. So all of the this here is 5 by 4, 2 by 8, etc. Right? And then what I do is that I sum it across the anti-diagonals, meaning in this direction. So if I go across this cell here, first answer is 5. Starting here now, I go across here. The next answer is 4 and 15, which is 19. Here is 2 plus 12 plus 20, which is 34. 16 plus 6, which is 22, and 8. Right? So here are my 5 answers right there. Yeah? Simple? Yeah? No, maybe? Good. Right? Which is as simple as that, right? So then you could express it graphically. So this graphical representation would have been X, of course, is 1, 3, and 4. H is 5, 4, and 2. And this is what the actual convolution looks like. Notice that the convolution, as we keep stressing, the convolution has nothing, no values in between here at all, right? It only occurs at these particular instances in time. Yeah? So one of the things you can do for homework very simply is to try to find the answer for this one. What is the convolution of this system? The system HNT is NT, T is 0, 1, and the output, sorry, the system transfer function is HNT, and T is 0.01, and the system input is e to the NT. So if I'm going from 0, it will be e to the 0, e to the 0.1, e to the 0.2, etc. So put those values and put them into the convolution table. So these are the x values and the h values here. So the x's will go so, the h's will go so, and then you fill in the answer. And when you fill it in, right, when you fill it in, you should get, first off, a table looking convolution sequence looking like the numbers below. And if you need to check it, what did we say? We have 4 values. X is 4, H of 4 values. X is 4 values. So that's 8 in total. So the convolution has to have 7 values in them, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Wait a minute. Oh, because it is 0, sorry. The 0 value ignored, right? So it really should have had a 0 in front of here, right? Technically. All right. So it's supposed to have 7 answers. One of the answers is 0, so it is not printed here. Look at right here. My mistake. Right, so that's the 7th one right here. Right, I'm getting cross-eyed. And then you can check this now. Just follow this here. Here's some MATLAB code. MATLAB has a function called conv, which is short for convolution. So this runs the convolution. Here's the code for that previous example. So it's generating X, it is generating H, and it is finding the convolution of X and H and plotting the answer for you. All right. So here are the numbers for H and X and the output Y. And you could check, you could see that the values would agree if you what do you call it, if you didn't make any mistakes in the calculations before. Right? So all of your values should come up to something looking like that. All right? Questions? Make sense? Yeah? And one of the things, funnily enough, is that because of this process, we can actually, those continuous time convolutions that we were doing in signals and systems manually, what you can do, for instance, if I were to tell you to find a convolution of a rectangle and a triangle, for instance, what you could do is to take 5, let's say 5 values of the rectangle and 5 values of the triangle, calculate those values. You still have to know the equation of the triangular pulse for argument's sake. So you enter the 5 values of the signal, you enter the 5 values of the, whichever is the one that you designate as a system and the signal, and then you could work out the values, and you're going to get 5 and 5, you're going to get 9 sample values of what the output should look like. So that could immediately tell you if the continuous time convolution, your answer was correct, including the time zones as well. Yeah? So I couldn't tell you that, or we couldn't tell you that in signals because we wanted you to do the integration. But here's how you could check your answers without doing it, without necessarily having to do the integration. Yeah? All right. So let me end here before I run into somebody else's class and they get annoyed. Let me stop the recording.